Welcome to another video. This is the pigeonhole principle. If you've never heard it, well, this is a good introduction to the concept. If you've heard it before, but you really don't know what it means or how to use it, well, you're going to see a very basic example here. Now, this is a principle that is profound in its consequences, but the concept is just very, very basic. And as soon as I explain it to you, you're going to understand what it is. I had to redo this video because there was a short part of the video which I really didn't explain well, and the way I did it, my mind was working faster than the concept I was trying to explain. So this is a redo, and let's get into the video. What exactly is the pigeonhole principle? Well, let's use pigeons and pigeonholes. Say you have 7 pigeons and you're trying to place 7 pigeons into 4 pigeonholes. Now, I want you to imagine what's going to happen. You have, let's say they're boxes, 4 boxes, 7 pigeons. Well, this principle says there has to exist at least one of those boxes containing more than one pigeon. Yeah, that makes sense because you only have 4 boxes. So let's assume you fill each of the boxes with 1 pigeon each. You're still going to have 3 pigeons in your hands. So, well, it's either you shove all the pigeons into one box, or you're going to put 2 here, 2 here, 2 here, and then 1 left. Or you can do 3, 3, 1. Or you can even do all 7 pigeons in one box if you're that mean. And then you leave 3 empty boxes, right? That's the pigeonhole principle. So what I'm going to do is write the mathematical statement, and then we'll talk about some consequences. Okay, this is the pigeonhole principle. If m is greater than n, that's a prerequisite condition. That's the first part, okay? If you have more pigeons than holes, then it's basic. If you place m pigeons in n holes, then at least one of the holes must contain m minus 1 over n plus 1 or more pigeons. So let's use the numbers 7 and 4 to explain this. So, example. If we place 7 pigeons in 4 pigeonholes, then at least 1 pigeonhole contains, this is the calculation, 7 minus 1 over n, we take the floor and we add 1 to it, or more pigeons. Let me write pigeons here. Okay, I'm going to explain that. Now, with the number, it is very easy for you to know. Not n, our n in this case is 4. So what we're saying is, if you take 7 pigeons and you're trying to place them in 4 pigeonholes, if you're a good guy, you're going to put 1 pigeon in each of the holes and you're going to have 3 pigeons left. And then you're going to say to yourself, well, I have put 1 pigeon in each of these holes. The 3 I have left, it is either I put 1 here, put 1 here, put 1 here. So I'm going to have 2, 2, 2. Or I'm going to put 2 here, 1 here, and these will be 1, 1. But the pigeonhole principle just says that there will be at least 1 container that contains this number plus 1. Now, what's this number? This is the floor, the greatest integer less than what you got, less than or equal to. Now, what you have here, based on our calculation, this is going to be 7 minus 1 over 4. So the number we're looking for here is the floor of 6 over 4 plus 1 or more. And what is this? 6 divided by 4 is 1.5. So the floor of 1.5, the integer that is less than 1.5 or equal to 1.5 has to be 1. That's the smallest, the greatest integer less than or equal to. So that's going to be 1 plus 1 or more pigeons. So there has to be one of these boxes or one of these pigeonholes containing 2 or more pigeons. If you place all the pigeons in the pigeonhole and none of them escaped and you didn't eat any of them, do people eat pigeons? I think so. Yeah, I don't know. I don't know. Okay. But that's the point. Now you go, yeah, that makes sense. There's no space. You have to shove them somewhere. Well, it is the implication of the pigeonhole principle that actually almost breaks people's minds because you get consequences that you never thought about. So a very basic consequence of the pigeonhole principle is this. Imagine you just finding any random gathering of 8 people, a group of, or number of 8 people, and you'll observe that at least 2 of them were born on the same day of the week, because it is either you were born on a Sunday or a Monday or Tuesday all the way to Saturday. So you've got 7 options, but there are 8 people. So the 8th person must belong to one of those other days. So there are 2 people in every gathering of 8 that are born on the same day of the week. The same day, same thing, you go to a classroom. Once the classroom is more than 31 students, then you have guaranteed there were 2 people who have the same birth date, may not be the same month, but the number of the day of the month will be the same. And there's a lot more coming. Actually, there's an International Mathematics Olympiad problem that was based on the pigeonhole principle, which I am still exploring. When I figure out how to answer it, I'm going to make a video on it. Okay, so that's it. Let me put a quick proof of this in this video. Let me explain what I'm going to do in the proof. It's going to be a proof by contradiction. You see, when you do m minus 1 over n plus 1, let's go from this consequence. So we're saying that our x will be greater than or equal to 2. That's the meaning of 2 or more. Okay? If you want to negate this, you want to say this is not true, you just have to find a value of x that is strictly less than 2. Okay? In order to get a contradiction, so we're going to say, let's assume this is not true. We just need to find a case where x is less than 2, and then whatever we're doing here is not right. So recall that x is less than 2 is the same thing as x is not equal or greater than 2. That's the meaning. Let's try to connect what I just explained here to the proof, because what we have here is we're saying that x is greater than or equal to, so we have x is greater than or equal to, this number is, let's just say, the floor of 1.5 plus 1. Okay, that's what we're dealing with right now. The number of pigeons that are going to be in at least one of the holes. Okay? But right now, what I want to say is, let's assume that we're not achieving this. We're not achieving this. This is what we're achieving. X is strictly less than 2. We know that 1.5 is strictly less than 2. So if I say x is at most, so if I say x is at most, the maximum is less than or equal to 1.5, if I can find x to satisfy this, we know it will never satisfy this, because we know 1.5 is less than 2. right? So if I focus on what is in the middle here, which is always less than this. So even if this was 2, if this was the number 2, this will always be x is greater than or equal to 3, so that if I change this to 2, this is still correct. This will never satisfy this condition. So I'm going to remove, which was the mistake I made on the previous proof. I did not remove the floor. So I'm going to remove the floor. We don't need the floor in this analysis here, because if you equate x to what is inside the argument of the floor function, your inequality will be correct. So let me erase this. I think I already showed what the consequence of this is. I'm just going to do the proof and do one universally experienced concept. Recall that the floor of m minus 1 over n is less than or equal to m minus 1 over n. So, right? That's actually the definition. This is what I would call my k in the first place. So let's assume, assume the maximum any box contains So we don't have that extra one that I said. So that's the maximum, because that's how you justify the inequality. Then all the boxes, okay, the maximum that can be contained in all the boxes, then the max in total is n times the floor of m minus 1 over n. This is multiplication. N times this floor. But we know that this see, this is less than this, so this has to be less than n times m minus 1 over n. Let's put this in parentheses. This is less than or equal to this, so we say that n times m minus 1 over n, take the floor of it, is strictly, no, is less than or equal to, if you multiply this by this, you're going to get m minus 1. So by the time you gather, if what we're claiming is true, if we assume that the maximum any box contains is this, which does not satisfy the pigeonhole principle, then it means that if we multiply that by the number of boxes, because let's say all of them are filled to the brim, but this is the maximum they each have, then it simply means that what you have here is less than m minus 1. But m minus 1 cannot be the maximum number of objects we have, because the maximum we started with was m, unless somebody has eaten one of the pigeons or caused it to fly away or something. So we can't lose pigeons, so this is a contradiction. It's a basic proof. This is a contradiction. Since we started with n objects. So that's the basic proof of it. Okay? The only mistake I made in the previous one is I ignored this and did not use the inequality. I just went straight to this. Okay? But this is even stricter than what I did. So let's look at one natural consequence of the pigeonhole principle. And this is a fact. If the population of a city is more than 1 million, then, come on, don't speak bad English. Then, there are at least 2 people in the city with exactly the same number of hairs on their head. That sounds ridiculous, right? But it's a fact. And this is how they came about it. Assuming you pick a random person and you can count the number of hairs on their head. Well, let's say there's a baldy somewhere and he has only 1 strand of hair. You're going to put that baldy here, has only one hair. If you ever find someone else in the city with one strand of hair, you put him in this category. You keep increasing the tally here. So tally, and then you put another one, and then when it gets to 5, when you find 5 baldies, you're gonna strike this out, and you keep building the tally. Then you open another box looking for guys with, or women with 2 strands of hair. That rarely happens. But let's say you got 2 strands, then 3 strands, then 1,000 strands of hair, and then 100,000 hairs on their head. You just put them in the different boxes. So how many boxes do you have to create? Well, it is scientifically impossible because of the size of your head and the thickness of hairs for you to have more than a certain number of hairs on your head, no matter how thin your hair is and the number of holes you can have on your head. Unless your head is as big as this house, then maybe you might have 1,000,000, but a normal human being would have hair strictly less than 1,000,000. So the number of boxes we can create, this would be for 2, this would be for 3 strands of hair, and then this would be for 4. You keep going until you get 1,000,000. But nobody has 1,000,000 strands of hair on their head. No, nobody. Maybe there is, we don't know, but there's nobody, not in this city. Maybe in your city. So this is it. Now, after you've filled in all of this, suppose we find somebody who has each of these number of hairs on their head, then the 1,000,000, see, if a city has more than 1,000,000, so the 1,000,001st person has to be put in one of these other categories. So that means that person and one of these other persons must have exactly the same number of hairs on their head. That is the pigeonhole principle. There are more complicated problems, but these are just very easy examples. There's an Olympiad problem with the number of handshakes you're gonna have, or birthdays or something, and we're gonna break them down as the questions come up, but that's it. So one of these has to be doubled, at least, okay? I think I read some comments in the previous video. The number of hairs on a person's head on average is between, I think, about 150,000, thereabout. Some people, the maximum ever recorded has been about 500,000, 560,000 or so. If you have any new details, leave in the comment section. I hope this was interesting and you learned something. Never stop learning. Those who stop learning, stop living. Bye-bye.